New problem. A coil through which passes a magnetic field B. Well, that's not even a complete sentence. Imagine magnetic field goes through a coil in the direction indicated in the image above. The coil diameter is 2 centimeters. If the magnetic field goes from 0.020 to 0.010 Tesla in 34 seconds, what is the direction and magnitude of the induced current? Okay, so it says induced current. So what deals with induced currents? Dangerous.
Induced currents, chapter 23. Inductance? Or RI? Yeah, because no, that's self-inductance, I was thinking.
Well, this is a self-inductance. A coil with a changing current makes a self-inductance. And so we have multiple ways of looking at this. One would be that V for the inductor is equal to L change in current over change in time, where L is equal to mu watt N squared. Boy, I actually don't have this memorized.
I can find it. I'm at the same section as where that is.
Where L is wait. You actually there's right there, yeah. U watt N squared. I'm missing the area. So that's one way of doing it. That's the way of doing it, just using, well, this is an inductor, so let's go with that. And then once you have the voltage, of course, you would say the current is equal to the current induced is equal to V over R.
Okay, yeah.
So that's one way of doing it. Another way of doing it is just going with Faraday's law of induction. Which is going to get you to the same equation. The minus sign is actually going to work out to be the same because it's dropping, but it's just the direction of the current, not the magnitude. And so you'd have minus N, and the flux is...
it's like the magnetic field times area, isn't it? Oh, no. Maybe not.
That was B times A. So that's B is the first one here. And it's technically B dot A.
Okay.
But of course, because the magnetic field is going to be parallel to A, then we just put a times A. Okay, that looks like a cross now, even though there's no vector signs. So there's the magnetic flux.
Okay.
And now if you look at the two equations, they come out to be exactly the same, except for the minus sign. N squared, because we have N times N, mu watt A over L times change in current over change in time. So you see that Faraday's law of induction it gives the exact same answer.
I just think that one's more straightforward.
This one here is shorter, which I assume is what you mean by straightforward.
Yeah.
This one here goes back to what's going on, why is it happening? So I prefer this one because we have the why is it happening. This one here is like we have a magical device. But it's, yeah, they're both getting you the same place. This here comes from, this leads to that.
Okay.
So with all of that said, then, we can just say the current induced is equal to that's taking this equation, putting this into it,
Mm-hmm.
is equal to L over R delta I over delta T. And so we need to calculate what the L is, or I can just put everything in here. Mu naught N squared A over length times R. Pi R squared, and they gave us diameter, right? Yep.
Mm-hmm. I've memorized mu naught.
Yeah, I had it wrong yesterday. I put 2 pi instead of 4 pi. I wrote 4 pi the first time. I was like, no, I think it's 2. I was wrong. So now we just put in our numbers. So mu naught is 4 pi times 10 to the minus 7. That's Tesla meters per ampere, right?
Yeah.
Times N, which they...
What's that?
Do they tell us N?
No. That's why I want you
Oh.
to use.
Well, okay, they told... I did all of this. They tell us the change in magnetic field.
Good job.
Yeah. Everything I did was correct except for it doesn't match what they gave us.
Yeah, we can just plug
Yeah.
B and A in.
So yeah, it's much simpler. Oh my goodness. So is... My phone is ringing. Well, actually, there is a problem, though. The problem is this has N squared in it, or N times B A. So we still need to know N. Or I guess we could say since B is equal to mu naught. No, that doesn't help us either. Mu naught I N over L. I could solve that for N in terms of B, but then I have I and L that I don't know. Without knowing A, I'm still going to get a value that's a multiple of N. So, I can get a multiply all of that through, mu naught was included in the B, so that's why I don't have that. 0.02 divided by 2 is 0.01. 0.01 squared is 10 to the minus 4. 10 to the minus 4 divided by 10 to the minus 1 is 10 to the minus 3. That is 10 to the minus 2, 10 to the minus 3, 10 to the minus 10 to the minus 5. That's a 34, not 39. So, there.
I might not be typing it in right, but I have 9.23 times 10 to the minus 7 for just what's in your parentheses.
It's what?
9.23 times 10 to the minus 7.
I wrote out the word amp so we wouldn't get it confused with area since I have N in there.
Yeah.
Let's do the one thing that we can get a definite answer to. What direction is the current going to be flowing? If the magnetic field is pointing that direction and getting weaker, then what direction does the induced magnetic field have to point?
It has to point the other direction.
No, because it's getting weaker, it has to point the same direction.
Oh, okay. So, are they looking for like clockwise, or are they looking for a right or left?
Well, let's just go with this. Is the current going up or down here? Is it going up or down here?
This one's going down, and that's going up.
You are correct, ma'am. In order to make a magnetic field that's going to supplement the magnetic field, since it's dropping, right? Because it's dropping, your induced magnetic field has to supplement it to try to keep it the same. That means your fingers go like this, so they come down on the side nearest us. This here is nearest us, so it's going to come down there, go up there.
So does that mean it's like clockwise? Or what are they looking for?
Okay, we have to look at the answers they give us so that we can determine that, because clockwise and counterclockwise wouldn't make sense in this case.
Okay.
You could say if I'm looking at the front or if I'm looking at the rear. So that's why I went with the ends.
Gotcha.
Going into the left end and coming out of the right end is what makes the most sense there. It doesn't have the direction there. It has a current value, so they assumed a number of coils. Maybe we're supposed to count them.
Yeah.
We'll do that in a minute. And it simply doesn't have the direction there, which is the part that we can do. I'm going to copy this problem here and then go back to count them and see how many are actually in the picture. So if we count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 that we read from the picture. So we're assuming this picture is very literal. And I think that is the answer they got.
I don't know how else we were supposed to get the coil number. 2, 3 times 10 to the 6. Wait.
that's the number. Well, that's more digits. The digits that you have is 14.768
Okay, you rounded.
times 10 to the 6. I rounded because
Yeah,
we only had 2 sig figs.
gotcha. Okay.
Alrighty. The figure shows a uniform magnetic field that passes through a closed wire. So this is a loop. It's got a bend in it. The wire circuit rotates at an angular frequency of blank. I swear I didn't cut it off. Yeah, there's no number there. Well, that helps a lot.
Yeah.
Look at our answers. U and K. People are really trying. I'm just going to put omega here. We'll figure out how that works. Graph the axis shown in the dotted line. Derive an expression for the magnetic flux through the circuit as a function of time. So what is the magnetic flux?
That is a magnetic field times the area.
Okay, magnetic field times the area. So what we have here is we have some angle, theta. Theta is equal to omega t, right? It's rotating at a constant rate. I know it shows it as 45 degrees here, but it just depends on when you set time 0. So just make it omega t and you'll be good. Magnetic flux through the circuit. If you do the magnetic flux, you're going to have, let's just say that we align it in the simplest way possible. So we have it like this with the magnetic field going like this. Then I would have the magnetic flux is equal to the magnetic field strength B times the area of the upper one, which is going to be L times L over 2, right? L over 2 is this dimension, and L is this dimension. So the area is L squared over 2. And then this one here, it's going straight in, so that would be, one of them is going to be cosine, one of them is going to be sine. This one here, the angle would be 0 degrees. I have cosine of that angle. This one here, it's going to be perpendicular. Right, so I have this one here has an angle that's 90 degrees different. The sine is what gives me the 90 degrees different.
Okay.
So if it rotates by 90 degrees.
What's cosine like? What's the angle for cosine?
Well, the angle is going to be the angle between the normal to the upper surface.
Okay.
So here is my direction for area 1. Oops, area 1. Here's my direction for area 2. And so at this angle right here, I'm saying this is theta equals 0.
Okay.
And actually, I suppose I have the sign backward for the picture I drew. I have the sign backward for the picture I drew because it's B is going one direction, A is going the opposite direction in that picture I drew. But it just depends on which direction you consider positive. So I'm not concerned about it. So that would be the simplest way of writing it. Now you can combine cosine omega t plus sine omega t. You come up with a sinusoid that's at 45 degrees and it has a different magnitude. But I'm happy to leave it right there.
Okay.
So that's the flux as a function of time. Now I have a student who's supposed to be coming now to have a discussion with me. Yeah, see they went ahead and did the it's not showing us the correct answer, but I'm pretty sure that this one here, oh yeah, it does. Yeah. That's what you get from combining the sine and the cosine.
Okay, so they're not actually wanting a numerical number.
No.
Okay.
Because they didn't tell us what b was, and they used a instead of L squared.
Okay.
And that's all the new ones on that one. So we finished